Hello, everybody. So glad to see everybody here today. We've got a lot of folks. This is great. Just want to make sure you guys can hear me. So if somebody could raise their hand or maybe type into the question box that you can hear me, that would be great. Yes. Okay. Thank you, Scott. All right. Well, hey, everybody. Welcome to the Stats for the Masses webinar, Communing with the Data, overview of descriptive statistics. My name's Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. Thank you for those of you who took the time to join us live today. And I'm going to present a review of an overview basically of descriptive statistics. So I'll be using SPS software for the presentation. Of course, you can run descriptive statistics on just about any statistical software. So I like SPSS. There's a function it has called Explore, and you'll see I really like it. It shows you a lot with just a couple clicks of a button. So it's just an overview today, but as always, I hope that the information you receive today will give you some ideas and guidance towards further research into exploring your data. As I say in all of our webinars, you use what you learned today, apply it in a holistic way. So look at your big picture. Descriptive statistics are the best way to get a good feel for what you're working with. And you should do this every time you first get a data set. Take a look at what you have and how it's all laid out. I've scheduled a total of 90 minutes for the presentation and questions. I don't know if it's going to go that long today. Really depends on the questions we have. Some people are not hearing me. It looks like it looks like Norma cannot hear me. Can other people hear me? I know Scott could. Sorry about that. There's some people that say they can't hear. Yes. Okay. Most people can. All righty. Okay. So I've currently muted the line so only my voice can be heard. So I'm not a great multitasker when it comes to webinars. So if you have any technical issues, I probably won't answer, but I often find that just logging out and back into the webinar clears up just about everything. So I just say, when in doubt, reboot. Okay. So let's go on and get started with things. So just a little bit about Omega Statistics for those of you who have been to other webinars or have looked on the YouTube channel at our different webinars that I have posted. You kind of already know most of this, but I'll just go through it for the new people. I am a private practice statistician. I have my own consultancy, and I'm in Southern California, Murrieta, next to Temecula wine country. I do medical and clinical research, so a lot of clinical trials, all the phases 1 through 4. I do a design and analysis of experiments. I do work in some epidemiology and with large data, and I also help with journal articles. A lot of researchers like to publish their work, and I help with that as far as writing up the results and also running the analyses. So I help with dissertation assistance. That's probably 50% of what I do. I typically methods and results chapter. I can help with all chapters. And if you look at the website, you can see the different levels of service you can have. I go from the, just coaching all the way up to, helping you write the things. Survey design, seminars and webinars. I have off the rack or custom made. So you can see the website, Mega Statistics website for more information on that. I do offer free ones every quarter. This is one of them. The next one we'll probably have in July. I'll take on most projects of any size. So I work with individual researchers. I work with small businesses. I work with government. So my motto is to provide elegant solutions effectively applied. So our task today is to obtain descriptive statistics for a data set. In statistics, we usually call it checking assumptions. Is my data normal? Are there any outliers? Things like that. In data science, it's often called exploratory data analysis, but it's a lot of it is the same thing. So I'll show you how a statistician does it, and it's quite a bit like the data scientists do it also. We just kind of have different names for things, really. So descriptive statistics and measures of variability are the big things. And descriptive statistics can be divided into measures of central tendency and also dispersion, and that's your variability, how spread out things are, how dispersed things are. Measures of central tendency are what's the center of that data? Usually we want, in most instances, as far as working with a normal distribution, which we're going to be looking at a lot today, we want that central tendency tendency, we want to know where the center is, what's the mean, what's the median, and we also want to know how far spread out things are from that center. And so for the central tendency, we're going to look at mean, median, mode, measures of variability. There's variance, there's standard deviation, which is standard deviation goes as basically strictly with the normal distribution. And then there's interquartile ranges. And so we'll be looking at some of those things today. And of course, you know, a mean is just the average. You sum up all your values for a variable, you divide it by the number of values you have, right? The number of records, and that's your mean. Median is the true center. That's where you have 50% of your measurements above a certain value and 50% below that certain value. That's your true center. So today, working with the normal distribution, and I'll show you some more when we get to the histogram. You really want your mean and median to be close in value, because that means that your mean is close to the true center. And if you see what a normal curve looks like, you'll see why that makes sense. A mode is just which number comes up most often, or which value comes up most often. So it doesn't necessarily have to be a number for a mode. You could have categories, you know, who belongs to, you know, what, like, I think I have an example with M&Ms in a bag, you know, how many, what color had the most representation in that bag. Okay. And of course, the variability is the dispersion, and we'll look at that a little bit more also. I think, you know, for this, what we're going to do is I'm going to go into SPS and I'm going to run some things, and we'll just go through the output from a data set and some information. And I think you'll get a pretty good understanding of how, what things mean, and I'll describe them more as we go. All right, so we have different data types. Okay, and here's a little hierarchy I made up. So here's your data type. Usually we have two main flavors of data. We have the qualitative, which I have over here just in a little corner basically, and then we have quantitative, which is what we're going to be focusing on mostly today. Quantitative data deals with numbers, things you can measure objectively, dimensions such as height, width, length, maybe temperature, humidity, prices, area, volume, all those kind of things you can measure, okay? Qualitative data deals with characteristics and descriptions. Can't be easily measured, but they can be maybe categorized or observed subjectively. So you might have smells, taste, textures, attractiveness, color, anything like that, and you're just going to fit them into different categories, okay? So broadly speaking, when you measure something and give it a number value, you create quantitative data. And when you classify or judge something, you're creating the qualitative data, okay? But this is just the highest level of data. There's also different types of quantitative and qualitative data. So for the quantitative, we will have discrete data, or we will have continuous data. Okay, those are the two types of quantitative. And we also can, you'll hear quantitative data referred to as numeric data also, because it's mostly numeric, okay? As a general rule, counts are discrete and measurements are continuous, okay? So discrete data is a count that can't be made precise, more precise. So it involves integers. So the number of children or adults or pets in your family, that's going to be discrete because you're counting whole indivisible entities. Even though you might hear things such as, like, you know, 2.5 families or 2.5 kids, typically you can't have half a kid, right? Or you know, 1.3 pets, you can't have a third of a pet, right? So that would be your discrete data. Okay, it's just counts, numbers. Your ordinal data, which we'll look at a little bit more, would also be considered the discrete. So continuous data here, on the other hand, it could be divided and reduced to finer and finer levels. So you can measure the height of your kids at more precise scales, or even yourself, right? You can get measured in, you know, feet, and then in inches, or maybe meters and centimeters, millimeters, beyond. So the heights continues. You could keep breaking it down. Another thing I like to say is, like, you know, you could be 5'8", you could be 5'8.5", you could be 5'8", 0.598, you know, 0.598 inches or something like that. So it can be broken down smaller and smaller, okay? For the discrete data, we have binary, which is two outcomes. It's usually yes or no, go, no go if you're in process control, things like that, either or, and it's usually coded 0 for no, 1 for yes, you know, or they're also called indicator variables. You'll see binary coding and something else called dummy coding. So these are just binary, either or, yes, no, things like that. Ordinal, for the discrete data, it's actually ranked, but it's not, you actually, a type of, even though ordinal and count data are kind of similar, ordinal data is usually more subjective, because ordinal data you'll see on things like the Likert scales, where you have maybe from 1 equals totally disagree to 5 equals absolutely agree, and then 3 is kind of I don't care, it's in the middle. So you only have scores 1, 2, 3, 4, 5, right? But my idea of a 3 might be your idea of a 4. Okay, so it's not really measured with a ruler or measured with some kind of instrument or something like that where you're getting a precise instrument. So ordinal's a little bit more subjective than a count, and it's a little bit more subjective definitely than just a, measure. You're not using a real measurement tool. So that's kind of the difference between ordinal and count. Then you have nominal. And that's, again, discrete. That's classifying, the colors, maybe the different colors of M&Ms and such. So it's just categories. Race, ethnicity is another one that would be nominal. There's no hierarchy to it. With ordinal, you have 1, 2, 3, 4, 5, maybe 5's higher. With colors or race, ethnicities, or, locations, things like that, you're not going to have hierarchy of any kind. You just have different bins, different classifications. So that's what the nominal is. For continuous data, we have interval or ratio, and this is kind of where people get a little bit confused on it. So as I said, continuous data can be divided and reduced to finer and finer levels. Okay, I like to think of continuous data as data that could have decimal points and still make sense. That's my favorite way of looking at this. Interval has exact order between the values, but it doesn't have an absolute zero. Okay, so something like temperature. You can add or subtract these numbers and make sense of them, but you can't multiply and divide for an interval. So for instance, if it's 10 degrees outside, and then I add another 10 degrees, I get 20 degrees, and that's fine, but I can't say that 20 degrees is twice as hot as 10 degrees. It's not like that. So it's not, that would be interval. Ratio has the exact order, okay, and it has an absolute zero value. So examples of that, of ratio, would be height, weight, things like that. And we can add, subtract, multiply, and divide because we have that true zero value. Okay, so the big difference between interval and ratios, there's not a true zero where it's like nothing. Right. You can have zero temperatures, but you can also go negative. In ratio 2, you can also go negative, but you could basically have it's more readily measured. So what are some examples? I have some examples here for M&Ms. If I tally the number of M&Ms in a bag, that number is a piece of discrete data. Okay, same thing if I count the number of each color of M&Ms. Now, if I use a scale to measure the weight of each M&M or the weight of the entire bag, that's continuous data. Okay, because we're measuring weights and we're actually using some kind of measurement tool to do that. Continuous data can be used in many different kinds of hypotheses tests. So we might want to assess the accuracy and weight printed on the M&Ms bag, so we could measure 30 bags of M&Ms, perform a one sample t-test and see if it matches that weight that's on the bag. Some analyses use continuous and discrete data together at the same time. So for instance, we could use a regression. We could have a regression model, and we could see if the weight of the M&M bags, which is continuous data, is correlated with the number of M&Ms inside, which is discrete data. Okay, so we could do something like that. Interval has that exact order between values, but not an absolute zero. So that's just like the temperature, like I said before. And then the other one, the ratio, does have the zero as a real value. Okay. Qualitative, I have over here in just a little sidebar here. It's a whole different type of analysis. I love doing quantitative studies. I do qualitative studies, but a lot of qualitative to me is writing. It's like writing a book to me. So I'd rather work with the numbers. Doesn't mean qualitative doesn't have numbers. It's just that it's a little bit, you look at it a little bit different way, right? You're not going to use it for hypothesis testing necessarily. Okay, so we do have binomial, nominal, and ordinal all also could be qualitative, discrete or non-numerical. Okay, so when we look at the data set, maybe we'll look at some of those and you can see some differences on the discrete versus the continuous. Okay, I think that's about all I have to say about this slide. I guess one more thing, uses of this ordinal data is a matter of debate among statisticians. Everyone agrees it's appropriate for creating things like bar charts, but beyond that, the answer to the question, what should I do with my ordinal data, is it depends, okay? Because sometimes you can take ordinal data and use it as continuous in some analyses. One author, maybe probably more than that, say if you have set of 5 categories on that Likert scale or that Likert scale, maybe you have 7 or more. You know, maybe you have a scale that goes from 1 to 10. Something like that is getting very close to being able to use it as continuous data. Some authors say if you have 7 or more categories on that ordinal, you can maybe go to continuous. Also, if you have another thing I should tell you about is like if you have a survey and it's all those 1 to 5s, from strongly disagree to strongly agree, and you sum up a bunch of those values into a score, now you have continuous data. And then you can use that in your models that use continuous data. So do we have any questions on the different types of data before we move on? Let's see. Okay, I have please give an example of using ordinal as continuous. Would the result be valid? It depends. Like I said, what should I do with that ordinal data? It depends, Norma. It's like the example I gave a lot of times for a Likert scale. If it's over 7 values, 7 categories, and typically you can, a lot of authors will say you can go ahead and use it as continuous. Or like I said, if you sum up a bunch of items from a scale, say maybe there's 10 items and they're all scored from 1 to 5 and you add up them and you can get a score anywhere from 10 to 50. Now you can go to continuous. So if you added up those Likert scores in Likert items, each of the items, 10 items, into a score, now you can do continuous. Does that help? Okay. Great. Okay, what else we have? Okay, so good. Let's move on then. Okay. So again, we have the 4 basic levels of measurement. There's the nominal, there's the ordinal, there's interval, there's ratio. Of course, there's 5 really. There's binary. There's other types too, but today we're just going to concentrate on these. So here we can see our measure of central tendencies. Okay, and what we could use. Okay, so if you have interval or ratio data, that's considered continuous. So you can find a mean. You can find the median, and you can also find the mode. Okay, if you have ordinal data, which is considered discrete, you really don't want to look at the mean on that because it's not. You don't really. It's not continuous necessarily, so you wouldn't go to the mean. Median, yes, you could definitely have a middle. Like, what's the value most people are answering, and in a mode, you definitely could say most people answered 4. Agree. And then that would be your mode. Nominal data, which is a discrete categorical kind of things, colors, race, ethnicities, things like that. You don't have an average. You don't have a median, but you could have a mode. We had more blue M&Ms in the bag. Well, usually probably not, but you probably maybe have more brown M&Ms in the bag, right? Than other colors. Okay, so you could have a mode. So the data set we're going to use today, I thought we would just go right in and start analyzing some things. I'd show you some descriptive statistics in real life, how I would work with the data set a little bit. Now, this is a pretty large data set. I'm certainly not going to go through and look at every variable, but I'm going to pick out a couple of them and we'll look at some things, maybe try to transform some things. We'll look at this kind of stuff. So this data set is patients, includes patients that are diagnosed with all stages of head and neck head and neck cancers, okay? And they were referred to a tertiary hospital, okay, and to the head and neck program for treatment during the years of 2002 to 2010. The study included a population of 1,055 patients that were diagnosed and treated there over the 8 years of study. A total of 5 cohorts were also looked at for the study. Each patient cohort followed a 5-year time frame. So we have cohort 1 that started in 2002, followed into 2006, and this N here tells you how many people were in the cohort. Okay, and so on and so on. The second cohort, 2003 to 7, third, 2004 to 8, fourth, 2005 to 9, fifth, 2006 to 10. And here's all the samples, all the little cohort sizes, and they should add up to the 1,055. Okay, so that's our data set. So before we get into the analysis, there's some 3 steps you should always take before you start playing with your data. Save a backup of the original file as you receive it before you do anything to it. Usually what I will do is whenever I receive data from a client, I will make a file for them on my computer. I will also make a subfolder called From Client. I will put that data in the From Client file. I will never touch that. That's in case I make a mess when I'm cleaning the data, or I do something wrong, or heaven forbid something happens to the data I'm working on. I don't lose everything, right? I always have that beginning point of the data clean, just as it came in before anything was done to it. Then you want to make sure you have a unique identifier for each record. In our example, each row has data for so we have 1,055 rows of patients. So each row should have a unique identifier. Okay. Unique identifiers are usually numeric, but they can be alphanumeric, colors, animal names. I don't care, as long as each record has a unique way of being identified. As you're going through your data, you're looking at your data exploratory data analysis. You're looking at your variables as you're cleaning it up. Maybe you need to fix some things, make some adjustments. If something is an outlier, how are you going to know which record, right? So you want to know which record you can go back to and look at, okay? Typically what I will do is I will save the file with unique identifiers along with that original file. You're hoping the original file comes with unique identifiers, but it doesn't always, okay? So I'm going to save both of them. But then I'm also going to save the unique identifiers file as a working file, and that's what I'm going to use to make any kind of observations or changes to my data. Okay, so I always have 2 pretty files put away somewhere nice, one directly from the client or one that raw data, right? And one that has unique identifiers with the raw data. Okay, so now I can feel comfortable and confident in moving on and playing around with this data set. Here's some easy ways you can make a unique identifier in SPSS. You just follow these steps, or you can do it with syntax. Okay, like I said, remember to save 2 files, one with the IDs in a safe place in case you need to reference back, and 2, that working file which you're going to use to run the numbers. Okay. Steps 4, 5, 6, and on through infinity. Back up your work often, right? So as you're running through these things and you're looking at stuff and you're maybe making changes to the data and stuff, back up your work, because there's nothing worse than working on a data set for a week and then having something go wrong and you have to go back all the way back to change something. We don't want to do that. So I'll back up at least daily. I'll back if it's something that's I'm really not sure about, and I'm really playing around with and going, oh, is this right? Am I doing the right thing? I will back up so often. It's it drives me crazy sometimes, as many times as I back up. But I'd rather have that than have to do work all over again. So back up your work often. Okay, so we're going to check the data today. We're going to look at the data. We're going to look and see how accurate it is, see if everything looks okay before we run our analyses, right? We're not running any analyses today. We're just basically running descriptive statistics. So we're not doing any kind of hypothesis testing or really inferential tests. We're just checking it to see if our data looks okay before we run our analysis, okay? So this is how you would go into SPSS to get the frequencies on your ordinal nominal variables. If you want to run measures of central tendencies for your continuous variables, you're going to do your analyze descriptives, or today we'll look at analyze explore, which is very, very useful in SPSS. We're going to look over the output, make sure all the data for each variable are within the right ranges and that it makes sense. It's important to understand your data and what we have, right? So know what you're looking at, commune with that data, right? So now would be the time to make corrections inside of each variable before you start combining them or transforming them or anything else or imputing them. If you have some missing data and you need to put some values in there, we want to make sure everything's nice and neat before we do any extra steps like transformations or imputations, okay? So let's look at some data. Let me go ahead and pull some up here. So I'm kind of just going to run around in here a little bit and show you some things. Let's see if I can pull this up here. There we go. I'm going to try the pointer again. Hold on a second. There we go. Make this a little bigger. Seems to be running a little slow today. Okay. Okay, so I'm looking at this data set from the hospital, and I can see right here, I don't really see any unique identification numbers. Nope. Okay. So what I'm going to do is first I'm going to make that ID number. So go ahead and go back here. I'll go back and copy and paste paste my syntax, but we can go into the transform. Let me get my notes here. See, I'm used to doing the code. So, but I want to show you how to do it on the menu. Okay. So we're going to click on transform. And then we're going to click on compute variable. So I'm going to give it the name ID. I'm going to put it here. Okay. And then I'm going to click on all in the function group over here. Okay. And then I'm going to drag and drop. Let's see, I'm going to pick case number. There it is. So I can double click it or I can drag and drop it over there. Okay. And so then I'm going to press OK. Okay, let's try it again. So we're going to hit transform. We're going to go compute variable. Now we're going to name this variable ID. So everybody has a unique ID. And then we're going to go here, click all, and then we're going to click double case number, and then we'll click OK. And there it is. Yay. Let's see. It should be here on the very end. Yep, there it is. 1, 2, 3, 4. So it just matches up with whatever the case number is over here. So it's case number 1, ID 1. Okay. So now everybody has a unique ID. And if we go down to the very bottom of the data set, we should have 1,055 records, right? And there's the last ID, 1,055. So now whatever I do, however I sort the data set, whatever I do to it, I'll be able to go back and see if I need to. I can look at the ID number, the case number, and see where there might be a problem. Okay, so that's the first thing you want to do. And then we would save this, okay? So I would save it just as the, with ID, maybe, save as with ID. Right, and we would just put it in our save in our go ahead and save it to my little shared folder here. I'm not showing you all my folder names because they have client names on them, so I want to make sure. But here's my webinar folder, so this is okay. So I'm going to save it in here. Here's my descriptive statistics, so I'll just call this guy working. And also I would probably have one that was with the ID that I would save too. Okay, so I'm going to call this one working. I already have one that's saved with an ID. We'll just pretend that. Okay. All right. So we have unique case ID. Let's look at this a little bit and see what we have. Here we have the different genders, right? Here I have the actual names of the genders. So these are categorical, males or females. But you can see here I also coded gender. So we have males are coded as 1 and females are coded as 0. Sometimes when you use some analyses, you need those numerical values to represent your categorical. This would be considered nominal. This is also considered nominal, but it's binary, right? Because it has a 0 and a 1. Okay, so it has 2 values. You can look at the regression webinars I have, and a lot of times you'll see the dummy coding and why that's useful. And the data cleaning, the GIGO no-nos, look at that webinar. It also will tell you a lot about the dummy coding. But sometimes I'll take these and I need to make them coded, okay? Here we have different credit ratings, their marital status, occupation IDs, as well as occupation descriptions. Again, these were given codes, okay, for and typically with a big data set, if you didn't make it, you should ask for a code book. You want to know what these variables represent, right? You don't need to guess at it. Some data scientists, they don't care, they'll just run it. But if you're a statistician, you kind of want to know what you're looking at. You'll have you want to know what your variables mean. Okay, so here I have them all. Here's their different races that are categorical, and here they've been dummy coded into 0 and 1s of whether or not they're white, black, Hispanic, or other. So if they're black, they're coded as a 1 here, and otherwise they're coded as 0. Okay. And there might be more here than that were coded, but this is probably all I needed for the analysis. Okay. Then we have ages. We have some different types of cancer. Where did they have it? Dummy coded. What I want to look at though, let's look at grand total. These are the costs for each year that the person was treated. Okay, 5 years for each record. So this person here looks like they had year 1, year 2, and year 3. They didn't stay there 4 or 5. Okay, here's the grand total here of what their fees were for treatment. So let's take a look at this variable. This is continuous, right? It's dollars. It's measurable. You can have $0, and it makes sense. You can even have negative numbers. It makes sense. You don't want to, but let's take a look at this. So what we're going to do is we're going to go into Analyze. Now you can go into descriptive statistics here, and you can click on descriptives, and you can ask for your descriptives for this. Let's see, grand total. I'll put it over here. There's some options you have. You can get the sum of all of them if you want. Like they'll add up every value in here. I rarely use that, but you definitely want the mean. You might want the variance. The standard deviation would be good to know. You want to know your lowest value and your highest value. Okay, maybe you want the standard error of the mean. You can click on whatever you want. You might want the range. Okay, you might want to look at skewness and kurtosis. Okay, well, we'll look at that later. And then we just display order. We just want to do variable list. Just leave it like it is. Okay, we don't want to, we don't need to worry about this. So just hit continue, and then hit OK. And then here's our output. Go ahead and take this out of here. Okay, so here's our descriptives. Okay, so we had the N. We had 1,055 records, and they were all here. So valid means how many actually had a value. So there was a number in every single record for the grand total. So we don't have any missing data, okay? The range was about $504,000 with the minimum for treatment of $1,628 and a maximum of $506,259. So it's a pretty big range. Somebody here had a lot of care, somebody here maybe not so much, okay? So here's our mean. Our mean is our average. It's 91,032, and their standard error is about 2,000. Standard errors used whenever you're computing your confidence intervals, and I'll talk a little bit about that. Or if we don't have time, I do have another webinar I'll refer you to where you can see the difference between what a standard deviation is and a standard error is. I think I had somebody ask me about that, so I do have a webinar I can refer you to. Here's our standard deviation. And here's our variance, huge. Variance is always big because standard deviation is the square root of your variance, okay? So that's nice. It tells us a lot of numbers, but I really like this explore, okay? So let's look at this one, and we're going to put in the same thing, grand total, okay? And then I'm going to want both statistics and plot, so I want to make sure this display both is clicked. Then I'm going to go into statistics, and I want outliers. I don't really care about these M estimators or things other than the mean that can be used as an estimator. I don't care about that. I don't really care about percentiles, but you could check that if you wanted to. Typically, I want the descriptives, a 95% confidence interval, and I want to see if I have outliers. So it'll give me box plots on that. Okay. Here's our plots. Stem and leaf is great. I like a histogram. I think it shows a lot better. A normality plots with tests. I'll go ahead and do some normality tests, and I'll tell you a little bit more about those in a minute. And then I'm just going to hit continue, and then options. If you have missing values, you want to click on option. If you have more than one variable in here, say I wanted to look at grand total plus all these, maybe these other years, and I wanted to get information on all of them separately, but maybe like we saw for some records, they didn't have all 5 years of numbers. If you exclude cases list-wise, that means any records that don't have a value on every variable that you want, that you have in this dependent list, will be excluded from everything, okay? If you exclude cases pairwise, then what that means is that if, say, a person had a value for year 1 and 2, but not 3, 4, and 5, or something like that, they would be included in the numbers for year 1 and 2, but not included in the years for 3. 5. Okay. In this case, we're just looking at grand total. We already know everybody's counted. There's 1,055 records, all with value, so we're okay. So it doesn't really matter. But just to be safe, I like to use pairwise. So in this case, it'll come up the same. And then we'll click OK. Now, a lot of this you can get in other softwares. You just have to use maybe different codes, syntax. You can do anything in R. You just have to know the code of it. And of course, any other statistical software will probably be able to give you most of this information, if not all of it. So now we have Explore, okay? And we have the grand total here. It's 1,055. There's all our records. Nothing's missing, okay? Let me see if I can get a better pointer here. Okay, so nothing's missing here, okay? And so there's our total. All right, so now here's all our descriptive statistics. Include, most of these are measures of central tendency and variability, okay? So here we have the mean, which is the 91,032 with its standard error. Here's our 95% confidence interval, okay? And this is found by the standard error, okay? The standard error, the difference between a standard deviation and a standard error is the standard deviation relates to the population you're trying to estimate. So say, for instance, we have these 1,055 records, but we want to kind of know, like, if we were looking at a whole population, like maybe all over the country of these, and this was just a sample taken from it, what would we estimate to be the spread of the true values in the population? Because when you do statistics, it's all guessing at the population. We don't know the value of everything in the world. In this case, we do. We have 1,055. That's all we have. But this is just for this one tertiary, clinic, one of these tertiary hospitals. It's not for all of them, right? So, so if this is a representative sample, and if we can assume that it is, which would be hard to do because you want random, but if we assume that it's it's a good sample, then we would say, okay, well then we're averaging. We would say on average for the 5 years of care, or a person that comes in for treatment, on average is going to spend about $91,000 on their treatment. Okay, and the standard error is going to tell you how close you are, or how precise your estimate of that $91,000 is. Okay, so basically, for a 95% level of confidence, you would take 1.96 and multiply it by the standard error. Then you'd subtract that value from this mean, and that would give you your lower confidence interval. And then you would add the 1.96 times this, and that would give you the upper confidence interval. And that would mean that you could be 95% confident that the true mean in the population is somewhere between 87,085 and 94,098. Okay, so that's our confidence interval. This is our point estimate. This is our guess, but we can be 95% confident that the true mean is between these two numbers. Okay, that means that we are 5% not confident, right? Because we are only 95% confident, and that's just the nature of statistics. We are guessing, so since we're guessing, we don't know exact, and so we always have to make a little bit of precision. We need to put a bound around our estimate to give us an idea of how precise that is. And on this case, you know, for something that's 91,000 and we have a standard error of about 2,000, that's not too bad, right? That's a pretty small standard error considering. And that's also a function of how big your sample size is. If I had a much smaller sample, your standard error would be much larger because you can't be as precise, you don't have as much information. So like I said, I have that standard error and standard deviation, little 30-minute stats in a snap little webinar. I'll refer you to that, and you can see more of this. And I'll even show you some, as the sample gets smaller, how the standard error grows. Okay. Then we have a 5% trim mean. Sometimes you might have outliers. In this case, we're going to have one. I've used this data set enough, I can already tell you we're going to have one. Plus, when you looked at that range, it went from what, 1,000? It goes from what, 1,000 up to 506,000. That's a huge range. So I'm assuming some people probably didn't have, there weren't, very rarely can you go to a hospital and pay just $1,000, $2,000, right? But often you can spend this much, 500,000, especially if you would have cancer. So I'm just saying though that looking at some other things here, I can tell that we're probably going to be off a little bit. Our mean, which is our average, is 91,032, but our median is 84,600. Okay, median. Oh, well, I'm sorry, that's the trim mean. The median 75,000. Okay, so that's a big difference, 75,000 and 91,000. The median is our true center. That's where 50% of the data is above that value and 50% of the numbers are below that value. Okay, but the mean is higher, quite higher than the median. So that's telling me that there's probably a high value pulling that mean up from the center. Okay, if I look down here, it'll tell us some extreme values. Okay, here's the highest extreme values. So they go from the top 5 highest, 506 is that big one, right, which is the maximum. Okay, and then it goes down to the top 5, it goes down to 383. So it looks like this person out here is going to be pretty outlying. Okay, your lowest values, though, we do have quite a few lower values, but the lowest value is this minimum, the 1628 right here. Okay, and then it goes up to the 5th lowest value is about 6,000. So not as bad, not like going by $200,000 from the 5 highest. Okay, let me get my arrow again. See if I can go down here. 1 second. Oh gosh. Okay, let me see if I can do it this way. Having such troubles today. I'm so sorry. Okay, here we go. All right, so we saw our extreme values. Let me see if I can erase everything. Okay. Here's a test of normality. You'll hear these quite a bit. What can I say about these? Tests of normality are fine. A lot of times you will report them, but what you see as far as your histogram and such will usually be different than what the tests are showing you. We have 2 of them here. This is the Kolmogorov-Smirnov and the Shapiro-Wilk test. Okay, there's 2 tests of normality here. This sig is our p-value, the sig value here, or is the p-value. If you have a p-value for these tests that's less than 0.05, that means that these tests are saying you don't have a normal distribution. Okay, if it's above 0.05, 0.05 or higher, that means that it's yes, you do have a normal distribution. Okay, however, for records that are over, for data sets that have over about 50 or 100 records, these kind of fall short, and they're always going to show significance. And we have 1,000 records here. So these are going to show significance and that you don't have a normal distribution even when you do, just because you have, it's overpowered is what we call it. And this test is what we call conservative, which means it's playing it extra safe as far as, saying you have normality or not. So take this with a grain of salt. Always check these tests. That's fine. But also take a look at things. Look at things. Look at the histogram. Look at these plots. Okay. Here's a histogram. And this shows all the pile ups of the data. Okay, here's our grand total. These are our dollar amounts down here. Okay, and here's how often they show up. Okay, so we have little bins. Like this probably goes from 0 to, oh, I don't know how much, but they go up. Here's 200,000. So we have little bins and they're all put in there, the different values, all for all 1,055 records. I can see right here that most of my values are popping up right here. Right? This is the highest frequencies. So this is our mean right in here. 91,032 is our mean. However, remember how I said that we had some high values? Here's some high values in here, right up here. They're pulling that mean up from where the median is, which was about 75,000. So we might want to do something about these, right? First thing I would want to do is go back and make sure that the numbers were correct. So I'd want to go back and, sort my data, look at the IDs, see where that problem is. And up here, it gives you the different case numbers. So I can go back up here and go, okay, for record 1024, okay, what was the value, was that right? And maybe go back to the client file if I need to, call the data control department if I need to, whatever I need to do to make sure these numbers are right. Now, if they are right, they're right. You have a couple options here. You can say, well, they're right, I should include them, right? And you can go ahead and in most cases, run your tests anyway. Normality is great to have for many tests like a t-test, regressions, ANOVAs, all these parametric tests that you do. Normality is great to have, but what's more important is if you have groups, is your equal variance between the groups. So like if you're comparing, say, males and females on their total cost, what would matter more is that the variances and the are similar between the males and females, more so than normality. And that's what we call robust. The tests are robust to deviations from normality as long as you have equal variances between the groups. Okay, so some people though they'll want to go ahead and change this, and it's possible that sometimes when you transform a variable, which I'll show you, it's great. It comes out beautiful. You love it, right? Other times it does more harm than good. It comes out worse. It looks worse. So you can try to transform, but again, transform first. Make sure your data is in good order, then run your tests. You're not allowed to go in and keep transforming and running tests until you get significance. That's cheating. Transforming itself is not cheating as long as you do it and get the distribution you want before you run your tests. Okay. We also have this normal QQ plot here. Okay, and it takes whatever the observed value was, which was the actual price, right, the actual cost, versus what would be expected for the value on a standard normal distribution or on a normal distribution. And what you have is this line here, and you want all the little dots to line up on this line. Okay, if they don't, that's an indicator that you're deviating from normality. And again, here's the skew. It's showing right here. It's this problem right here. It's showing, it's moving it away from this line. So we did pretty good down in here in this area, not too bad. Maybe a little skew down here too, right? And so at the ends, we're having a little bit of problems, okay? So the detrended one I don't really look at too much, but I do look at the box plot. Okay, so down in here, we're going to have our average and our medians and means down in here, this line. Okay, up here are all those outliers that are up there in that histogram. These values up in here. Okay, they're showing as outliers. And we don't like outliers too much. Okay, if they have this little star, that means they're an extreme outlier, which is more than 3.3 standard deviations from the mean. Otherwise, you'll just see them marked with a circle. And these are all their case numbers, which is great because if I'm looking at these outliers, I don't want to have to go back and try to figure out who in the data set is the outlier. Okay, so I'm looking at this and I'm seeing I might have some problems here with the normality. I have outliers, I have skew, right? Here's a skew here. I always think a skew is like a dog, okay? And here's its tail. So here we have right skew. If we had left skew, the tail would be going towards the left. This right skew is because we have these high values up here. People always ask about skewness and kurtosis on your normal distribution, and we have these numbers here. Skew, you'd like to have a number somewhere between -2 and +2. So we're okay here with the skew, actually. Kurtosis, you'd like it to be around 3 for your number, okay? Kurtosis is how pointy this is, and it's very pointy, okay, because you'd rather have a normal distribution that looks, let's see if I can try to draw something pretty here. You want something that looks like a nice symmetrical, it's supposed to be symmetrical, and here you want your mean down the middle, right, in here. Okay, you want your mean right in the middle, and you want the equal numbers. Just you want your mean right where your median is. Okay, in this case, that's not happening, right? We have some skew, but it doesn't seem like the skew is a big problem. But this is showing that kurtosis where it's really pointy. Okay, typically when you have something that's really, really pointy, you're going to have these outliers. If you have something that lays more flat like this, you're not going to have so many outliers, and your tails are going to be fatter. Okay, so something like this, I'm going, all right, we might have a little bit of problems here. So in this case, I might want to do some transformations. Okay, do we have any questions on these basic statistic kind of things first before I show you the transformations? I have Jason wants to know more about the standard deviation and standard error. I'll refer you to the other webinar, Jason, if we um, when we're done with this, and you can look at that. But does anybody else have any problems on any of this output that I've showed so far? Okay, we have okay. Okay, I guess everybody's doing okay. Well, good, and hopefully I'm doing well. Okay, let me go ahead and erase this out of here. Okay, so we have that. All right. So I'm not really, really happy with this. I don't know. I think maybe I might need to transform this. Okay. For whatever reason. Okay. So there's different kinds of transformations. Okay. The first one you might want to try, and typically is tried, is a log transformation. Now you can use log 10, or you can use the natural log, which is a log with the base E. Okay. The natural log statisticians like, because we like to, when we do our math, if you take the natural log base E, you can make things disappear. Okay, taking a natural log of E is going to make that disappear and just give you whatever the exponent is. It's just something mathematical. So we like to use the base E, which is a natural log. Another kind of transform people usually use are square root transformations, and those are best for counts. So if you have, like, number of people that come to a counter during a certain amount of time, or you have, the number of blue M&Ms in the bag, things like that kind of distribution, then you're probably going to use the square root. You can use the square root on a continuous too, and I'll show you. And then there's other transformations. There's a lot of them. You can invert transformation, but I don't usually recommend that because it makes this distribution turn the other way, which is bad. There's arcsine transformations, which you would use for a percentage. But today we'll look at the log and we'll look at the square root if we have some time. Let's look at the log transform. That would usually be the first one to go to. So I'm going to go into transform. I'm going to go into compute variable. Our favorite here. I'll just go ahead and reset this. Okay. And now we're going to let's call this log. What was the name? Grand total. Okay. You know what? Actually, I'm going to call it LN grand total because I'm using a natural log. Okay. So now I'll go over here into this box, and then I'm going to click on my statistical function group. Nope, it's not there. Let's go back up into all. It'll be in here definitely, and I'm going to go down to LN. There it is. And see right above it is log 10 if you wanted to do that. Okay. So I'm just going to have the LN there, and then right here where that question mark is, I'm going to replace it with grand total. Okay. Then I hit OK. And then when I look at my data set, it'll be on the very end. Here's my LN grand total. Okay. So let's go ahead and run this and see what we have. So I'll go in my descriptives, go to explore, And now I'm going to take this out, and I'm going to put in LN grand total. Okay, everything I'm keeping the same. Okay, so nothing, I'm not changing anything else. I'll click OK. And let it do a little work. Okay. Same thing up here, right? We didn't lose any records. We shouldn't. Now our mean is 11.17. Okay. I look at the median, it's 11.20. Oh, I'm a little bit happier because that mean and median are very close, right? And my confidence interval still looking pretty good. Again, we take that 1.96 and we multiply it by the standard error and we subtract it from the mean for our lower bound and we add it to the mean for the upper bound. Okay, 5% trim to mean is if we took 2.5% off the top and 2.5% off the bottom, this would be our new mean. Not too different. And again, I like looking at the mean and median. This right here tells me that we're doing pretty good. When we look at that histogram, I'm expecting to see something better, okay? Our variance, standard deviation, our minimum is now 7.40. Our maximum is 13.13 because we're on the log scale. And that's a problem with transformations is once you transform them, now you have to explain dollar amounts in the term of logs, right? And that makes it hard to do. You can do back transformation. It's not always accurate because you're dealing with things called the geometric mean versus an arithmetic, the regular mean. A regular mean where you just sum up all the numbers and divide by the number of things you summed up versus a geometric mean. So they're a little bit off. Geometric mean, I think, is always less than the regular mean. Okay, so but it'll be close on a back transform if you want to do that. But you can also just report it this way. Another thing you can do is report your raw data, and then of course in your write-up say that you had a problem with normality and you decided to log transform for analysis. Okay, so you can still get all your descriptive information and still say all of these ones that were up here, use all these numbers for your descriptive statistics, which is what we're looking at, and then just say for the analysis, we're going to look at them. We're log transforming them for analysis. Stream values, again, you know, things just don't make much sense now whenever you log transform. Again, now we're looking at the test of normality. They still are saying that we have no normality, that it's non-normal. But again, it's a very large sample statistically speaking. So these tests are going to fall short on us. But look at this histogram. That looks much nicer, doesn't it? I mean, if you look at the difference here, here's the old one, had that skew, right? And it was all piled up down here. Well, now it looks good. Now, you know, it's not so bad now. Okay. It's let's look at our skewness and kurtosis up here. Our skewness is looking very good. Our kurtosis is nice now too. Okay, because we want that skewness between -2 and 2, and we want that kurtosis around 3 or so, but it's, you know, now it's a little flatter or so than we would like, but it's definitely not 5. It's not huge, right? So that doesn't look bad at all. I would say that's good enough, but now it looks like we might have some outliers on the lower ends because of the log transformation. Okay, but it sure took care of those upper outliers. Okay, here's our QQ plot, and look how nicely they're lining up on that center, on that line going through the origin now, or you know, through this 45-degree angle line, lined up on there, very nice. You know, a little skew down here. Okay, maybe a little up here, little things, but nothing bad at all. And here's our box plot. Now we have, it's showing quite a few down here that are lower and not so many upper outliers, okay? But our center's looking really nice now, and see our whiskers are kind of evenly above and below the center. So I'm liking this transformation better, okay? So I might use that one instead, okay? Let's see, I have one here where I have the square root. Let me see what we have with the square root. I already did it, so let's go ahead and put this back. I had already ran the square root, and you do it the same way you do the log. You go and you pick it and you give the square root. Okay, so let's go ahead and look at this one and see what it does. Okay, now we have square root. Okay, so now our mean's 284. Here's our standard error, very small. Okay, confidence interval is very small. That's very nice. That's very precise because this is what we're guessing the true mean to be, and we could be 95% confidence that it's in here somewhere. If we were to go out and pull another sample and do it the same way, okay, with a different group of people and from the same population, okay. Minimum, maximum, not so bad. For skewness and kurtosis, both look okay. Now my test normality, of course, are still going to say significant, right? But that's beautiful. That looks, in real life, you're not going to get this too much. You're going to always have some outliers. Okay, you're always going to have some kind of problem. Real data, I always say, is mean, ugly, and nasty. Okay, so you're going to have some problems with that, you know. But boy, we transformed it with the square root. It looks pretty good. And again, this looks good too. Okay, how do our outliers look? Not so many in the lower, still a few up here. So on this one, the log or the square root, either one would be good. I like the square root a little bit more, I think. Okay. And then you can look up some ways, you can Google ways to back transform if you wanted to back transform confidence intervals and such. I'm not really going to go into it too much today. We need to look at some frequency statistics now. Okay, so do we have any questions on the, like the normal distribution and measures of central tendency and variability for that? Yeah, Scott did say that normality is often more important with regards to residuals and not individual variables. That is true. That's why I said if you have the variance the same between two groups or 5 groups, or if you're doing a t-test or an ANOVA, if you have equal variability between your groups, you're fine. I wouldn't worry about normality really at all. If you have a regression model, you're going to look at something called the standardized residuals, and you can ask for that in SPSS with a plot. You can look at my multiple regression webinar, and you'll see that we look at that. And if you have a nice scatter of residuals, then you don't have to worry about the normality too much because you have that what is called homoscedasticity of your residuals. Okay, so yes, that is true. Thank you, Scott. Does ln mean that transform? Let's see what this is. What's this here? It looks like Jason's asking a question. I see does ln mean that transform, but I don't see the rest of your question, Jason. Okay. All right, well, let's move on then. I think we're doing pretty good. All right, let's go in and look at some frequencies. What do we want to look at? These are pretty easy. Let's look at, Jason said, does ln mean transform? No, it's just a type of transformation. Let me go back up here into the transform, okay? This is when you're transforming any kind of variable. You're going to give it a new name, and then here we transformed it with the ln, which was the natural log, okay? You also could do log 10, which would be this LG10, and transform it that way. That's a different transform, okay? Also, you could go in down here, and you probably have square root. If not, you can just take the square root, right? I think, yeah, here's SQRT. You could do SQRT and then get the square root, okay? And just hit OK, and then you would get the square root. Of course, you'd want to change this to square root, right? But it just, there's different ways of transforming, okay? And I don't think they have arc sign in here. I don't think that would be, oh, they do. Yeah, look, arc sign. Okay, so cool. So you can get the arc sign if you have percentage data and you need to transform. Okay, so that's all it is. It's just different types of transform to make this distribution look more normal. Okay, if that's important to you. Okay, and in a lot of cases it is. And this, yes, it's definitely, we're looking right now at the normal distribution mostly. There's all other kinds of distributions, but when you're using things like the t-test, ANOVA regressions, you want that, the normal distribution is what it's based on. Anything that involves linearity or the normal distribution would matter. This would matter, okay? Let's go ahead and look at some descriptives for frequency. So you just go into Analyze, Descriptives, and Frequencies, okay? These are much easier to look at. Let's go ahead and look at race, ethnicity, okay? And so we'll just put that over here as a race description as our variable. For statistics, you could ask for quartiles, things like that. This doesn't make any kind of sense because this is just a categorical race. We don't have to worry about quartiles or anything like that. They're not numerical, right? It's not ordinal. It's just, this is just a nominal categorical variable, okay? We don't need a standard deviation or variance on anything like this, right? Because again, we don't have that numerical kind of thing. The only thing that really might matter here in the central tendency might be mode. You can't add up race ethnicities. You can't find a median or the mean, but the mode might be important, right? Which one showed up most, okay? And then, of course, we don't care about skewness or kurtosis, okay? This value that are group min points is you would use, oh, it's kind of hard to explain, but say you had ordinal variables, say age group, right? And you had like 0 to 20, then you had like 21 to 40. So what you would do is you would say the group midpoints values, you would say for group 1, even though it goes to 10 to 20, I'm going to give it a number 10. That's the midpoint. Okay. For the second group that goes to 20 to 40-year-olds, I'm going to give it 30. Okay. So you would want to check that if you have that instead, but we don't. Okay. So we're just going to click continue. Okay. Charts. Oops, that's statistics again. If we do charts, oh, let's look at everything. Let's just look at some things. Histograms aren't really going to make too much sense here. Okay. So we're not going to use that one. Okay. So we're going to use pie chart. Oh, it's just going to let us use one or the other. Well, let's use bar charts. Bar charts are good. Okay. And you can ask if you want frequencies or percentages. Okay. Well, let's ask for the frequencies and we'll hit continue. In the format, we don't need to worry about this. I'm not going to worry about any of that. And style, that's only if you want to change some things like the way that it looks, but I'm not going to worry about that. So that's about all we need to do. Hit OK. And now we're going to look down here at frequencies. So let's go down here. Pretty easy. Here's going to show us how many records were included, how many were missing. Everybody had a race, so that was good. Nobody's missing, okay? Then here we have the different races that were included. So we have American Indian, Alaska Native, there's 2. And Black, there's 92, other 33, Spanish surname 119, and white is 809, okay? Here's the percent. Here's something called valid percent. If you did have missing data, you would have something here that would show missing, okay, and it would give you a percentage. So you would have the percentage of everything for here in the percent column. You would have, let me get my little spotlight thing. In this percent column here, you would have something that showed missing and give you a percentage. So what you really want to look at, if you're just looking at valid percent and you don't want to look, you don't care about the missing values, you'll look at valid percent. Here we didn't have anything missing, so they're the same. Okay, cumulative percent is just adding up the percentages. First, we started at 0.2%. Then when we added in the Black race ethnicity, we had added in 8.7. So 8.7 plus 0.2 is 8.9. Okay, then we added in 3.1, got us up to 12.0, so on and so on until we get up to 100%. Okay, here's our bar charts. Okay, as you can see, you can hardly see anything there. There were only 2 people. Here's our frequency counts, right? And here's our different categories. So Black there, other, Spanish, but quite a few white, right? And 809, so it's right about there. Okay, and that's basically it for something like that. Let's see if I can find one that doesn't have everything in it. So I can just show you that missing because that kind of trips people up a little bit. Yeah, let's see. We'll try a couple of them, see what comes up. So we know race had everybody. Oh, let's see. Let's look at marital status. Let's look at occupation, maybe description. And let's see, maybe their stage. Okay. Hopefully some of these will be missing. Let's see. Okay. Everybody's included except for this stage. Okay, so here for our marital status, nothing missing. For the occupation, nothing was missing, but the stage had 18 records missing. Okay, so let's go down and look at those frequencies. Look at all of those different, that's interesting. These are all the different occupations, right? So when you're doing analyses, as you can see, a lot of these occupations only have one, so there's going to be probably, there's no way you're going to keep a separate category of one for any kind of inferential test, any kind of, hypothesis testing. You're going to probably be combining, which we call aggregating some of these variables into bigger groups. With these smaller numbers, right? So that's part of the work. That's part of the data cleaning work, right? But now we're just looking to see what we have and make sure there's not any kind of strangeness going on. Let's go down to, here's the different stages, 1, 2, 3, and 4. These are the ones that were there. Let me see here. So frequency, these are the ones that were in stage 1, had 128, stage 2 had 142, stage 3, 182, stage 4 had 585. And that makes sense because a tertiary care hospital is usually the hospital that you go to kind of, I hate to say it, kind of as a last resort, right? They're the specialty hospital, like a cancer treatment center or something like that. So, you're going to have a lot of stage 4 in there. Okay. But we also had 18 missing. So what it does is it totals up everything you have here, but then it shows 18 missing, which is when you look at the percent, see how it's included in there? They include them. 1.7% were missing to get to their 100%. Now for the valid percent, we're going to say we're not including these missing. We don't care about them. We only include about the valid values. And so then we're going to give them different percentages. Okay. So instead of taking here, this is the percentages as relates to 1,055 records, which is all the records, even though there were some missing. This one is how it relates to the 1,037 records. Okay, so we didn't include the missing. And then the cumulative percent is also going to go with your valid percent. Okay, so that kind of throws people off a little bit. But your valid percent, unless you care about how many you're missing, right? And you do. I mean, anything more than 5% missing is the rule of thumb, is when you might be concerned. Okay, but here we're okay. We only had 1.7%. So, but that's how you would look at these, And again, the bar charts. Here we can see most people were married. Okay, and you can go back up here and look at your frequency tables and get your numbers. Okay, 738, 70% were married. Okay, 12% were single. Okay, and so on and so forth. Okay, so the frequencies are pretty darn easy, but the measures of central tendency and variability with the descriptive statistics like that are something else. What else should I show you? Should I show you a scatter plot? Let me show you a scatter plot. This is also useful to look at, just to see if there's a relationship between two variables. Okay, so we're going to go into I'll do a correlation and I'll do it with a scatter plot. Let's see if we have the bivariate. Okay, correlation. And let's see, let's look and see if there's a correlation. Oh, let's see. How about between months to death, okay, and the price? Okay, let's look at that. And it should cost more the longer it took, the longer you were in there, okay? So let's look at, where's our grand total? Let's look at these two. Correlations, you look at two variables, okay, and just see how they're related. So we're going to ask for Pearson's. Spearman's you would use if you didn't have that nice normal distribution or if you had ordinal data. Okay, in this case, grand total is numerical. It could have decimal points, right? So that's continuous. Months to death is time. Time is continuous. You can have months, days, hours, minutes, seconds, so on and so on. Okay, so we have two continuous variables. We can use Pearson. If you have an ordinal variable, you want to go with Spearman's. Okay, if at least one's ordinal. So again, we'll go with that. Options. Do we need any options in this one? We'll exclude cases pairwise. Okay. Which makes sense. If you have values on one and not on the other, it's going to exclude the cases pairwise anyway. So if any record doesn't have one of these on their record, then that means they're not going to be included in the correlation analysis. So we'll hit OK. Okay, here's our correlation. Correlations, Pearson correlations, not too much. Okay, here we have months to death is in our row, and we go over to the column grand total, 0.069. That's a very small correlation. It's not significant. Here's that sig. Two-tailed 0.284, that's greater than 0.05, so we don't have significance, okay? So yeah, we don't really have a correlation, but if you wanted to look at a scatter plot of it, you're going to probably see a big scatter and not a line. So let's go in here and look at graphs. We'll look at legacy dialogues. I'm going to go into scatter dot, and just a simple scatter. I'm going to define it. So let's put on our y-axis, let's look at the grand total. Okay, it doesn't matter which you want to do really. On the x-axis, what did we have? We had their months, right? Months in the hospital, months to death. Okay. And then we can hit OK. And look at this. You have months to death. A lot of people died probably within, a couple years there, and the price kind of went up here. You almost can see that there's a line in there, maybe, but the scatter's so great that you really don't have a correlation. I can kind of put in a line if I want to. I double click on this and I can ask for a line here in the center. Yeah, so I want to look at the linear, and then that's okay. And see, it's almost flat. So that means almost no correlation, okay? This is the line of best fit through all that data, okay? This is the best fitting line. There's no correlation. So that's not a really good example, but there are some, times you'll get a scatter plot and you want to see how they're related, and you're going to see a nice line, or you're going to see a nice scatter going up or down. And now there's another webinar I have on correlations that you can look at. We're just looking at the descriptives today. I don't want to get too much into, now let's go into a regression model. That's going to be too much for today. But so you can look at some graphical things like a scatter plot too, and kind of give you an idea between two variables. Okay. So yeah, we have a lot of different things that you can look at for these. So I think that's about it for me to show you. Here's some references to learn more on standard deviation for standard error. You can go, here's a place to start for more information here. And then watch this video. This is a YouTube video I was talking to you about. I think it was Jason that had the question, or I think it was Jason. But this is the back to basics video. About 15 minutes in, there's an example. Oh, that's how to find a confidence interval. Okay. I thought I put in, maybe it's on the next page. You know what I will do? I will send it in my follow-up email. I will send a link to the standard deviation versus standard error. I thought for sure I put that in there this morning, okay, but I do not see it. But it's on the YouTube channel for Omega Statistics, so you can just type in Omega Statistics YouTube, and then you can find it. It's a standard deviation versus standard error, and I think it's a stats in a snap video, and it's about a half hour. But it's something to look at, and it's we don't have time to go through it today, but you can look at it and let me know if you have any questions, okay? You can email me. I'm happy to answer you, and leave a note on the video on the YouTube channel. I'll definitely answer you. I love talking about this stuff. Keep in touch, stay informed. You can sign up for our email list, okay? You can either, or send me an email saying you'd like to be on the email list, and I'll add you, or you can go to omegastatistics.com if this link doesn't work when I send you the handouts, okay? And there's places on my website near the bottom of the pages where you can sign up for the newsletter, okay? Then you'll get notifications of events like this, other updates. I also have paid webinars that I do and seminars where I travel, and you want to meet me and come to a big seminar, that's fine. And I say almost weekly. I try to do a stats grab bag every week, and it's just things that I'm a private practice statistician. I have a practice, so I work with all kinds of different statistics and clients, and so every week there's something new I like to share just about. So depending on how busy I am, I try to get that out. You usually get it over the weekend or the Monday following the week. But yeah, it's great, and it also gives you all the information on upcoming events as well as some interesting statistical things. So I'm going to announce the next Stats for the Masses webinar in my follow-up letter. I don't know, with the way things are going now with all this, sheltering in place and stuff, maybe I might do some more than once every 3 months or so. But I'll let you know and see what the interest is on that. Okay, so I think that's about it there's some information you want to reach out to me. And any more questions? We have 5 or 10 minutes. I can stay a little bit later too. I don't mind. So any more questions? Okay, so I love having everybody here, and I'm glad everybody attended live. This was great. I had quite a few people today. So definitely ask me if you have any questions. You can always follow up. With me via email or however. And if you have any ideas for future webinars that you'd like me to cover, I'm happy to hear about it. And I'm always looking for ideas. And boy, everybody take care of yourselves. And I wish the best for everybody. And thank you again for coming and have a great day. Okay, bye-bye.